Alrighty, so what do we got here? It looks like it's afternoon. So I'm trying to close out resonance, trying to close out the whole bonding, first year, post-secondary bonding type of discussion. There's a few videos put together. The crude, handwritten organizational chart. See if we can get this to focus a little better because it's not cooperating. So let's see. Well, that brought it into focus for now. Okay. So we were talking about, I can make another note right now anyway, just so I can truthfully say I captured it on video. Technically, this is called a non-quantum model versus a quantum model. Let's just say that my way of separating it into quantum, non-quantum was simply the fact that everything over on this side categorically, well, obviously the real quantum treatment has to use quantum mechanics itself, so that's done. But when you get into valence bond theory, the one thing that this does use, has to be used, clear cut. You start with the atom when it's by itself. You look at its valence atomic orbitals. So the concept of and plus, once that atom approaches some other atoms that it wants to bond with, when the bonds are started to be made, you need unpaired electrons. You reconfigure, hybridize, so you're getting a new atomic orbital, a hybrid orbital, and then the two atoms overlap electron density. So I guess all I'm trying to say here is this is built off of atomic orbitals and atomic orbital overlap, which is clear as day, very, very, very much related to the quantum model of the atom itself. The quantum model of the atom is sort of pseudo kind of isolated from these types of models. Yes, there are aspects of Bohr-Rutherford diagrams or even Lewis theory itself, such as the octet rule, that are indirectly, in my opinion, related to the quantum model. They have a few things that can link up with, for instance, how many bonds something can make, which is related to what the quantum model clearly shows better. So that's my distinction for that. So in any event, we finished this whole chart, and if I was going to add something sort of at the bottom of it, it's the idea of resonance. I could have put the concept of resonance somewhere on this chart because resonance with one E, you need to talk about that. The thing about resonance is there's going to be essentially two important parts of this. One, in most first-year textbooks, they show resonance where the idea is drawings of resonant structures. And it's the idea of equal Lewis structures. Remember how we left off with one of these past videos where we can quickly use the valence bond hybrid model to quickly come up with the required number of unpaired electrons. So we're not following the Lewis procedure, but the end result is an acceptable Lewis notation style structure we can draw. So instead of using the Lewis procedure to get there. So the point is, if you can have equal resonance structure drawings of something, that's one way of showing it. So for instance, for this, I could show a quick example where we could take the carbonate anion. Now, we already talked about the oxyacid generic procedure, how to draw it, so we can employ that one first. We have 3 oxygens. Equally pass out these negative charges to the oxygens. The remaining oxygen that does not have a negative charge, because we ran out of them, you make a double stick. So we've drawn one acceptable resonant structure or Lewis structure, but as soon as you have a double bond versus a single bond, You asked the question, if we were magically keeping track of oxygen 1, 2, and 3, so we secretly labeled them, or something like that. The question becomes, and let's call this structure 1, to draw another equal Lewis notation 1, but we're going to move the double bond. Does oxygen 1 have to be the double bond 1? It could have been oxygen 2, so we'll draw that. But the equal structure would require that oxygens 1 and 3 get the negative charge. So this is structure number 2. And then we could say, well, we're playing this game. Another equal potential drawing is if carbon 3 got the double bond. So this is clearly the idea. There's 3 possible Lewis structure style drawings of the carbonate anion, dianion. And the point is, what they find out is none of these are correct. In fact, experimentally, if you wish, or even quantum mechanically calculated, what they find out is each of the bonds between oxygen and carbon are totally identical. So you're not going to find that one of them is double and one of them is single. So the concept, we'll talk about bond order. The bond order of the double bond is 2. The bond order of a single stick, BO, bond order, is 1. So the other way of talking about bond order is this a double bond, is it a single bond, or as we'll soon to see, is it a triple bond, right? So that's what bond order stands for. So one of the things we can do with that is we could say, look, you have, pretend those oxygens, you've got 4 sticks. So it would be like if you had 4 brownies, right? And you had 1, 2, 3 kids. Well, you've got to divide the 4 by 3, right? So, and I don't have a calculator, and let's see if my math here is going to work. So 4 divided by 3, that's 1, right? So then you get to be 3, that's 1, that's 10. So 4 brownies. So I'm going to divide the 4 brownies by the 3 kids who each won an equal piece of the 4 brownies. So you're going to get 1.33 repeating. So what they found out in reality, in the way that they show equal bonds, they draw dotted lines. So take a wild guess what each of these 3 bonds has a bond order equal to 1.33 repeated. Why? Because you have 4 available sticks amongst 3 kids or 3 oxygens. And if they equally share the 4 sticks, you're going to get a 1.33 bond. It's not a single bond, it's not a double bond, it's a 1.33 bond. And they're all equal. So they divided the remaining 4th stick equally amongst themselves. They each got 0.33 of a bond. This is now called a resonant hybrid, meaning all 3 of these are in one. But quantum mechanically, it makes more sense if I just treated it this way. 4 sticks between 3 kids, equally shared, this is what you're going to get, a 1.33 type of bond. The second problem is, and this is why some people would do this, and they say, this beast is going to have a -2 charge. But the reality is, quantum mechanically, they also say, hey, we have the same problem over here. You've got 3 oxygens like 3 kids, and just like a candy or a brownie, you only have 2. So this was the 4 brownies, and that was the sticks. There was 4 sticks. I could do the same thing with the charge. You've got 2 for 3 oxygens. So 2 charges gets divided by 3. Well, 2 divided by 3 is going to be 0.666, 7 repeated, 6 repeated. So 2 charges divided by 3. So another way of drawing it, to make the full-blown resonant hybrid, each oxygen gets the two charge split three ways. So it gets a negative 0.667, negative 0.667, and a negative 0.667. And this is very real. The electron density, quantum mechanically, calculates out to be very real and looking a lot just like this. So the final drawing, if you're asked on your exam, draw the possible resonant structures of carbonate, 1, 2, 3, so you have to draw them. Then it's going to ask you to also draw the resonant hybrid with the bond order and charge properly labeled, which is this one, right? So that works for that. Now notice how I split this up, and I just demonstrated what resonant structures, hybrids, bond order, and charge idea, how it's done in many textbooks. And it's related to how many suitable Lewis structures you can draw. This is still true, but what I'm going to talk about here is organic uses this plus mechanism arrows. Okay? So what I'm going to show you here is this analysis is pretty much what I'm going to expect on the exam. And this is under the concept of resonance, okay? So you can simply redraw this, and it's almost as if you're not even worrying or trying to keep track of what is a sigma orbital or sigma bond and what is a pi bond, okay? However, resonance, as it's going to be applied in our organic 1, 2, and 3, mechanism arrows in organic, in the concept of resonance, you're going to see how the two of them blend together. So yes, you're going to show possible Lewis structures, if you will. That's true. But you're also going to show how one structure can go to the next using mechanism arrows. So if I was to redraw this using mechanism arrows, it would be something kind of like, yes, I'm having coffee to try and stay alive. Okay, so organic mechanism arrows slash concept of resonance. Okay, this is not needed for 151 first year chemistry at the moment. This is meant to show you so you don't panic and faint when you see it and say something like, oh, I've never heard or seen that before, right? So this is done as a preemptive strike, if you will, to prevent that. So carbonate, if we have this, if this is organic chemistry, we quickly point out the hybridization of that carbon, as we've already learned last video, is sp2. This oxygen is sp2. One of these is a pi bond. The other one is a sigma. The key in organic is the pi bond, because when you break this, right, each of these has a p orbital. So part of the idea of organic is to watch the movement of a p orbital if you want to make one. Now the other acceptable Lewis structure, which I didn't bother drawing in a minute ago, but I think by now, when in doubt, you know you should draw in all of the lone pairs. So we're going to migrate this one, and it's the pi bond one, and it's going to go, this oxygen is taking these two electrons that make that pi bond, and it's going to put it onto itself. If it takes these two and puts it onto itself, you'll be left with a single bond, and these two, do you see how you get 1, 2, 3, 4, 2 lone pairs at the moment? Well, when the third one comes on, it'll look just like these ones. And then this one, because this carbon can always make 4 sticks, if you're losing one of the sticks, this carbon, so for instance, I'll show you the halfway movement. I'll show you just this one arrow. I'll show you in 2 partial steps what's normally done in 1 step. You would have, right, that, and that. And you would have 1, 2, 3, 4, 5, 6, right? Now, but notice, remember over here, this carbon, here's another electron, here's another one, here's another. This carbon originally had 1, 2, 3, 4 electrons that were its. If this oxygen takes these two up onto here, making its third lone pair and hence a negative, that robs this carbon of electron that it brought to the party originally. It's only left with its 3. So therefore, this is left with a positive charge if I left this drawing this way. So now the next thing is, I wanted to make this oxygen have the positive charge, so I'll take these two and I'll have it fall down just like that. So what have we done? We have successfully done this. So this carbon now has 4 electrons back, and that's why it no longer has a positive charge. But notice what we've done. Normally, we would draw these 2 arrows, normally, and I'll show it down here. This is the 2-step, just so you can really follow what's going on. We would normally go like this and do that. So in one step, we show both these arrows to give us this drawing from that one. But this is okay, showing breaking down your steps. So using mechanism arrows, all we've done is went from one acceptable resonant structure, which we previously called structure 1, to the number 2 one, right? And if I was going to show how we get to the other one, then we would say this one, right, could take those electrons back, and then this one could say, I want the double bond, right? So that would show the third Lewis structure where this oxygen has the double bond. So this is our third structure, just like we showed in one thing here with no arrows. This one shows the arrows, and we started counting a little more closely all of the electrons and the bonds and everything to find out who gets plus and who gets negative, and we're ending up with that, right? So in organic, this is how we would show that. In another example of organic saying draw a resonance structure, what if you had a carbon, this is an aldehyde functional group, and let's say this was a carbon and this was a last carbon with a methane. So we know that carbons in organic chemistry, carbon always makes 4 sticks, right? This carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4. We always know the stick counting type thing in organic. But if we were asked, draw possible resonant structures for this. Well, what we know in organic, this is specific to organic where you see this type of thing. I don't think first year textbook normally would ask you, now maybe if you do, what are the possible resonant forms of this? Each one of these drawings is a resonant form, and there's 3 of them for carbonate. For this one, and right away we notice the same thing. We're going to start looking in Organicville and say, the oxygen is sp2, carbon is sp2. So in organic chemistry, so somebody could say, what are the resonant forms over here? Well, when you have single sticked structures, they're really, unless you have access to something nearby that has p orbitals involved, you're not going to really see it. So one of these is a sigma, the other one is a pi. So what we could do, we could take these and put it on the oxygen, and this double arrow means resonant form, and that's why I should have did up here, right? The double arrowed thing, it shows you these are resonant drawings in organic, and I think even in first year. So we put a resonant arrow, and you would get carbon, oxygen now. And remember, one of these electrons belong to the carbon, which brought 1, 2, 3, 4 to the bonding party. That's why it was neutral here. But if that one electron carbon brought to the party gets stolen up here, this gets a positive, or formal charge, they'll call it, right? So, and this oxygen gets a negative charge. Why does this oxygen get a negative? Well, look what happened over here. Oxygen comes to the party with 1, 2, 3, 4, 5, 6 of its own electrons, sharing 2 of them. But now it's taking 1 from this carbon, acquiring it. So this oxygen now has 1, 2, 3, 4, 5, 6, 7 electrons. 1 more than the 6 it normally has to be neutral, therefore it is a negative charge. These are 2 resonant forms. So in other words, what they're saying is, if somebody writes down a picture of this aldehyde, and we normally write it like this, the bond order in this drawing looks like 2, but the bond order over here looks like 1. And the real thing is something in between. So it would turn out that the bond order, quantum mechanically, of an aldehyde, because of this resonant form, the bond order is probably something like 1.99999. And what that means is it's basically this drawing for the most part rather than this one. Okay? To give you a better example of organic resonance, just to finish the organic sidestep, organic resonant preview. Again, preview meaning you don't have to learn this in first year specifically. You can kind of see this and go along for the ride. One of the classics is an amide, NH2. This can go down to a carbon. We'll make it 2 hydrogens, and we'll just finish it with a methyl group. So here's an amide functional group. A carbon-oxygen double bond with this nitrogen, but the nitrogen has a lone pair. Okay? So if I drew this properly, you'd have 2 hydrogens, because nitrogen likes to make 3 bonds. At the moment, this is sp2, this is sp2, this nitrogen is sp3. And we already know, ping, 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 nitrogen, when it's by itself, looks like this. And we know that it's always going to hybridize when it's bonding to other things. 1, 2, 3, 4. It'll be sp3 hybridized. 1, 2, 3, 4. 3 bonding sticks. So here, one of them is to the carbon, right? Using one of its, and then 2 hydrogens come in. So this is what nitrogen hybridized is going to look like, and there's your lone pair. Okay, so now what we already notice is, but here's what's interesting. You need p orbitals available because of hybridization. This has 1 p orbital used to make the pi bond, right? This has a p orbital used to make a pi bond. This one's sp3 at the moment, but the interesting thing is you have a lone pair. So this lone pair can have a tendency to do this as this pi bond breaks and puts the 2 electrons onto the oxygen. So what you're going to get is a resonant form. It's going to look like this. You already had a bond here. This one is now going to change its hybridization to sp2, and it's going to make a pi bond. So one of them is sigma, the other one will become pi. Right? But notice, this nitrogen comes to this bonding party with 1, 2, 3, 4, 5. We know it comes with 5. If it takes this lone pair, throws it down here as that carbon one is leaving, because carbon can only ever have 4 sticks at a time. So as it comes down here, you're going to make a pi bond. This rehybridizes to being sp2. And it lost ownership of one of its electrons, because as soon as these 2 fall down here, do you see how one of them is now belonging to carbon? So this one only has ownership of 4, therefore it has to get a positive charge on it. Now the carbon, these 2 electrons, it lost 1 electron of its own, but it gained another one from the nitrogen, so the overall thing is a swap. That becomes negative. This is carbon, CH3, and this is HH. So, to make this look a bit cleaner, in organic, we would write this looking like this. right? We leave out the symbol carbons and hydrogen, so you know that the end is a carbon. Anytime you see a turn like this with nothing written, that is another carbon. And we automatically know, we fill in the 4 sticks with hydrogens ourselves. So this is what it would look like, and we're going to draw a resonance. So this can go up, and this lone pair can go in here. So what you're going to get looks like that. Now, somebody could say, draw the resonance hybrid. Well, this looks like it's a double bond. This was single, but now this looks single, this looks double. So the reality is you're going to get something quantum mechanically in between. Oops. I got to draw the dashed. Like that. And in this drawing, we have no choice but to now say, okay, what they found is the bond order of this, this one is not single, but it's not double. I think that the bond order of this one is something like approximately 1.6, if I remember. So it turns out that this contributes heavily. And what it means is, if this was a single bond, you get rotation around this bond. But they've proven that because it has some 1.6, not exactly 2 character of a double bond, there's limited rotation about this bond. That's why proteins, which use amide bonds, they have restricted rotation about this. And as far as the charge is concerned, this one here has a positive charge. So neither one is neutral. This one is going to have a certain amount of negative, and this one's going to have a certain amount of positive. Exactly how it's distributed, you'd have to calculate that. But the overall molecule, the whole thing is still neutral overall, right? So this one might have, instead of +1, so it's not fully all the way this way. So I'm going to make this number up. What if the positive charge here was like approximately plus 0.4? Well, therefore, this is going to be approximately negative 0.4, so it offsets and be neutral. That's showing how the charge, positive and negative, can be distributed according to what quantum mechanics says it will be. So that is a nice look at organic style resonance, and one of the most famous ones is benzene. So if you tracked 1, 2, 3, 4, 5, 6, some people would say, look, that looks like a single bond right here, not double. Well, it can resonate so that what you get is this, and we know that the resonant hybrid is this, because all of them, right, you've got 1, 2, 3, 4, 5, 6 spaces, 6 bonding connections for 3 double bonds. So it's like 6 spaces wanting, you're going to divide the 3 by 6. So that's one half. So each of these is going to be like a 1.5 bond order, right? And the other way of drawing it is benzene. That's what the circle stands for, this resonance. So each of these bond distances are identical and the same. So that's another type of it. So now what I'll do is I'll coming back to how we started. So for the last few minutes, I was taking a careful preview look at organic use of mechanism arrows and the concept of resonance, okay? And how lone pairs and p orbitals are being used. The normal way we look at it is simply drawing the possible equivalent Lewis structures, draw the resonant hybrid, and then even divide the number of sticks amongst the atoms taking it, divide the charge by the numbers of atoms taking it to draw your final resonant hybrid with bond order and charge distribution. So that being said, let's do another example, PO4 3-. So what we have here, using the rules of oxyacids procedure, you draw that, you draw out, connect 1 stick per oxygen first, you distribute the 3 charges amongst the oxygens, and the last one standing without a charge will double stick it. So that's it. So obviously then, we can, now what you're supposed to do is draw in all these dots, right? I said that in class. It's hard to make yourself draw them in, but that's what you have to do. This one has the double bond. We could have just as easily drawn it here, right? I'll leave out the dots, but you can draw those in. Okay, but we still could have put it here. It's equivalent. And we could have even put it here. So we have 1, 2, 3, 4 equivalent Lewis type structures. And what we're really looking at is which one of the oxygen gets the double bond. They each could take a turn at getting it. And all of these equally contribute as their wording to what is going to be the resonant hybrid. So you draw in this. You're not going to draw 3 single stick bonds with 1 double. They're all 4 of these regions of electron density are going to be the same. So the bond order is going to be equivalent. So you draw in dashed lines showing that they're not pure single. So what do you have? You've got 4 oxygens fighting over 5 bonds, 5 sticks. 4 children fighting over 5 donuts. So divide that. So what do we got? We got 1. This is embarrassing. 4. That's 1. It's on video. Such pressure. Longhand division. Who does this anyway? How many 4s fit in 10? 2? 8. Ooh, this is going to work out. So 10 is 2. Bring down another one. That's 20. 5. Ooh, 1.25. So the bond order of each of these is 1.25. So it's not like it's a double bond. This would have a bond order of 2 because it's a double bond. A single stick would have a bond order of 1. These ones have a little more than just 1 stick. They got a little extra. Each of them gets another 0.25 of a stick. And now we move on to, we had 1, 2, 3, a -3 charge. So you got a charge of 3 being fought over by 4 oxygens. So, well, how does this work? Decimal, line it up. How many 4s fit in 30? This is embarrassing. 7? Leaving it 2. Ooh, there's a 20. 0.75. So each of these gets a -0.75 equally distributed. Equally distributing the -3 charge amongst 4 little children or oxygens. Right? This is the acceptable resonant hybrid with the appropriately labeled bond order and charge distribution equally amongst the 4. So I think you get how this works, and you can see how with sulfates it's going to work. It could be SO3, 2- if that exists, etc., etc. So the oxyacids are a popular choice for showing resonance. So I think, folks, we've shown resonance for both typical first year Lewis equivalent structures, and we even did show quite a bit of the organic mechanism arrow preview. So I think that concludes that.